Hey everyone, my name is Ivan, and today I'm going to walk you through some of the recent developments in deep learning for natural language processing. So, here's roughly how the talk will be structured. First, we're going to go through a brief introduction, what the problem is, what the solutions that we're going to look at are. Then we're going to talk about something called word vectors, which is the idea of representing words with points in n-dimensional space. I'm going to go into that. And then we're going to talk about something called transfer learning, which is also a very cool idea. And then briefly, at the end, we're going to cover limitations of the current state-of-the-art natural language processing algorithms. So just like a couple sentences about me, currently a tech lead at a company called Heap. We're an analytics startup based in San Francisco. Half of our engineering team is remote, so I'm the only person working in Bulgaria. We like people from all over the world, so it's like part of the fun of it. Before that, I was a tech lead and one of the founding members of Limpom's Sophie office. Limpom is the company where the keynote speaker from like just before this lecture worked at. And then before that, I've been at Google, Facebook, and some other companies. Okay, just a couple of disclaimers before we go ahead. In case there are people who don't understand Bulgarian, there will be a couple of demos in Bulgarian, just to try to show the technology of how these things work with like something that's like more closer to our language. But the rest of the all the actual context of the talk will be in English, so you get all of that. And then the other is that if someone is like deeply into deep networks, so if someone is like very familiar with architectures and expects us to go deep here and all that, this is not gonna happen because we're not gonna have the time and it doesn't seem like the right place. So like there won't be a lot of discussion of actual network architectures. We're gonna talk at like high level what they get used for and how they get trained. All right, so with that out of the way, let's talk about the terms in the title of the talk. The title was Deep Learning for Natural Language Processing. So what is natural language processing? Natural language processing is kind of a catch-all term for any like problems that relate to natural languages. What is a natural language? Well, a natural language is one that is basically spoken and used by people and created by people in a natural way. As opposed to, for example, say something like C++ or Java, which is not a natural language. And it's like a completely different problem to process languages like this because they have structure, they have specific rules, whereas natural languages don't actually have that. Like there are a lot of rules that we learn in school, like here's where you put a comma, here's how you use like articles and that kind of stuff, but none of them are like very strictly defined. So like, for example, a lot of the rules that we have in Bulgarian get broken when you introduce words that come from English, for example, like the way that you do articles on them or you do multiple, like plural versions of these words, they get broken. Like the rules are not strict. So it's kind of hard because in order for a machine to learn to process a language like this, it kind of has to infer the rules on its own, and also it has to infer the exceptions and the exceptions to the exceptions and all that. So it's not a very trivial problem. And just to give you an example of what natural language processing could include, just talking to like voice assistants have been very much, I think, over the last few years. And just talking to something like Alexa or Siri or what have you includes at least like 4 different natural language processing problems. One is speech to text. So you say something, the voice assistant needs to take the audio that you said and convert it into words. Then it needs to take the words and use language understanding in order to understand what you're actually saying, like what's the meaning of this sequence of words. And then in order to respond to you, it needs to use language generation. Again, like the same process in reverse. You need language generation in order to generate the sentence that's gonna be returned to you, and then you need to use text-to-speech in order to turn this into audio so that you can actually get the return text response. So you can hear what the voice assistant is saying. And like there are a lot of other problems. This is just an example. And then the other term in the title of the talk was deep learning for natural language processing. Deep learning is a subset of machine learning that uses deep multi-layer neural networks in order to model the underlying data. So for example, here maybe we would put all the words in a sentence into a machine learning neural network and have that learn to model the language somehow. neural networks have been around for maybe like 70 years, but actually making them work for like networks with multiple layers and for a lot of the training data has mostly been a thing for the last maybe 15 or 20 years for a bunch of different reasons. One is that people came up with new algorithms that allow these networks to train better, and we also have like much more powerful hardware and a lot more data lately. So basically, today we can think that the problem space, like the set of problems that we're trying to solve is natural language processing, so like different things that relate to natural language. And then the solution space is deep learning. I'm making this distinction because there are other ways to solve natural language processing problems, like there are non-deep learning algorithms as well. Today we're going to mostly discuss deep learning ones. But for context, we're going to start with the classical one, just so I can give you like a basis for comparison for how the deep learning ones look like and why they do so. So a classic pre-deep learning approach to NLP is something called Engrams, which is the idea that we're going to model language with sequence of n words when n is like some fixed number. So for example, here we have n to be equal to 3. And for example, if we have the sequence, so we have the words dogs, love, and we want to predict what the next word is. Basically, we're trying to predict, for example, how likely is it that after dogs love, we're going to have the word walking. So to get the sentence dogs love walking. And the idea with Engram language models is it should take a huge body of text. For example, you take all of Wikipedia or a lot of news articles or something like that, and you model this probability by counting how often we had the phrase dogs love, and then how often we had the phrase dogs love walking. So you can think of it as of all the numbers, all the times that I saw the phrase dogs love, how often did it continue with the word walking? And model that as like a probability, use that as a model to model language. Now this has a bunch of limitations. It's basically trying to model the language by counting, which if you think about it, it's not actually what you would do if you're trying to think about language. Like you don't count things and how often you see dogs laugh and how often it's followed by walking. But it has like a bunch of limitations, and I'm going to talk about one specific one mostly here today. And this is that Engrams don't generalize. What does that mean? It means that it means that if we have the probabilities for the sentence dogs love walking, and so we can determine how likely it is that walking will be the next word after dogs love, this doesn't actually tell us anything about the sentence dogs love running, which if you think about it, it's almost the same. It's exactly the same in terms of language structure, and running is a pretty similar word to walking. And if you think about it in terms of knowledge of the world, dogs actually do probably love both, but our model doesn't know anything about that because it's only based on pure raw counts. So for example, if we trained the model with Wikipedia data, and Wikipedia data only had information about sentences that said dogs love walking, we would never know that dogs love running is also a valid continuation of that sentence. So basically, the problem is that Engrams can't model the fact that words can be similar to each other, even though they're not the same word. So it doesn't have the concept of walking and running being similar to each other. So one of the first things, like one of the foundational things we need to do in order to make deep learning work for language is to basically encode word meaning in some way. There are exceptions, like there are other things you can do, but this is used in a lot of the state-of-the-art models. So basically, we want to model somehow that walking and running are similar words. We want to teach the model to be able to tell, oh, when I see walking and running, those two words are similar. So if I'm able to put walking in some context, for example, after dogs love, then I should be able to put running in a similar context as that. And a way to do that is to use what is called word vectors. Basically, the idea is that for each word, instead of representing it as a sequence of characters, so say W, A, L, K, I, and G for walking, and similarly for running, we would represent each word as a vector or a point in n-dimensional space. So if you imagine having like a large n-dimensional space with like a lot of dimensions, you'd put points in there. It's kind of abstract. I'm going to give you an example that's like a bit more concrete on the next slide. But basically, after we have points, like in each word is a point in that space, we can basically treat word similarity, so what are these two words similar to each other, as are the vectors that represent these two words actually close within the space. So we have like, if you imagine that we have like this space and it's like goes from here to here, although like space is usually infinite, but anyway, like if you have a word that's like here and here, a pair of words, those will likely be dissimilar. And if you have something that's like very close together, those would likely be similar. And like a very high level way to think about this. As a more specific example, imagine that we have a three-dimensional space where the three axes are, x basically says, is it a movement? The y-axis says, is it fast? And z says, is it red? And then you can think of, in this three-dimensional space, which is like a super simplified example of how words could live in a space. Basically, you can think of it as each axis, like the how far along each word is along a given axis, basically gives you the answer to the respective question. So for example, if a word is far on the x-axis, so it's like far to the right, then it says that our model thinks that this word represents a movement. If it's high on the y-axis, it means that our model thinks that it's fast. Whatever it is, it's like represents something that's happening fast. And on the z-axis, then we have it's red. So in this made-up space, you can think of walking as having 0.9 on the is it a movement axis, so it is very much a movement. 0.3 on the is it fast axis, so it's like kind of fast but not very much. It's like it's not crawling but it's not running either. And then on the is it red axis, it has 0.1. Basically, it's not really red, whatever that would mean. And then for running, we would have like similar numbers, but instead of y being 0.3, which represents it's kind of fast but not really, we have 0.9, which says oh, it's actually pretty fast. And so in that kind of model, we'll actually be able to tell that these two words are more similar than words that, for example, are not movements at all, or things that are very red, or stuff like that. So we have this three-dimensional space, and we put words in it, and then we use some kind of distance between the points that represent the words in order to determine whether these words are close to each other or not. Now that was, like I said, the simplified example that you can think of. In reality, most models use something like a 100 to 500 dimensional space. So it's hard to think about 500 dimensional spaces. If you learned linear algebra in university, that probably helps. Otherwise, just imagine that there's like 100 high-level concepts or ideas, and we represent each word as how much it actually corresponds to each of these concepts. And then after you have this representation, you can use the word distances, the point distances as vectors. And the other important thing is that instead of having predefined dimensions, like before we had these movement, fast, and red dimensions, we actually let the model learn those. So we don't go ahead and like say, oh, I'm going to represent the words using these 500 abstract concepts, but you have the model learn them in a way that the model thinks is useful based on some target that you give it. So we're going to move on with a demo with one such model trained on the Bulgarian Wikipedia. Going to try to show you how things look like in terms of word similarities. For the non-English speakers, I'm going to do subtitles in English or whatever. All right, so the idea is that here I'm going to give it a word, and it's going to tell me in this 100-dimensional space what are the closest words according to distance. So, for example, we can start with something simple like no. And what we see here is that no as in like 1, the number. What we see here is that all of these represent some kind of counting. So it's like some, all, one of them, and then different forms of no of 1. So the model like kind of learned that things that represent counts are somewhere close to each other in space. Then if we have something like Chuvek, like a human, we say we have individ, it's like the closest word to Chuvek. Then we have mush, like a man, and then we have different forms of a human. And then we have a patient and God, in case that's what you were laughing at. Yeah. And then if you have something like, we had examples about dogs. If we put a dog here, we have an animal, and then pig, and then some other forms of, and then we have a baby for some reason. But that's what the model learned. Maybe there are baby dogs in Wikipedia. And we have, for example, president. We have like very important titles. So it kind of learned what the political structure kind of is. Like it learns that the vice president is close to president, premier, and what is that? I'm not sure what the word for that is in English, or like a leader. Like the model learned that all of these are similar in the vector space that it used to represent the words. And then, for example, if you put like a verb, like bjagam, I'm actually not sure what's going to happen here because Wikipedia doesn't usually have verbs. Oh, okay. So it does have other verbs, and then some other things. Bia, bia. And then an example that I kind of like is if I put chocolate, like a chocolate here, the closest word is actually chips, which I like to interpret as the model learned that junk food is like close to each other in vector space. So like things that are nice, like you enjoy eating them, but they're not actually good for you, are close to each other in terms of what the model thinks. If anyone has anything that they would like to try, now's a good time. If anyone has words or anything, go ahead. Programmistor. It's appropriate. There's a botchik, and then computer. And then we have Adobe, which apparently is very similar to a programmer. I can take one more, I guess, and then continue with time. Was that Jena? I think the model has bias on that, because it has things like this. So I was thinking of not showing that, but yeah. So that's actually an important topic in natural language processing lately, is that if you train the model on something that has a lot of bias, the model actually learns to represent that bias. So for example, if Wikipedia, the articles in Bulgarian Wikipedia often correlate woman with a Rubinia, then the model is actually going to go ahead and learn that, even though like maybe we don't want the model to learn that. Maybe we don't want it to represent that. That kind of bias, in that case against women, is actually kind of encoded in the model. And there are like interesting things that have been happening with that. For example, Microsoft like maybe 2 or 3 years ago, released a Twitter bot, which was supposed to learn from what people tell it. And then like maybe literally 2 days after that, it became like a racist Nazi that's like super aggressive to everything. So they took it down because it learned what people were telling it, and those were like Nazi and racist things. So yeah, that's like an important subject. We're not going to talk about it too much more here, but yeah. Okay, moving on. This is like roughly what the model learns in Bulgarian. Cool. Okay, so now we have word vectors. What do we do with them? And since we're talking about deep learning, one very popular thing that we can do is we can take these numbers. So now, like the word vectors are basically, for example, if we represent each word with a 100-dimensional vector, that basically means that we have 100 numbers. Like for each of the 100 dimensions in the space, how much does the word vector, like how far along is it along that dimension? So basically, we have 100 numbers, or 500 numbers, or whatever. And we can use those as input to a neural network, like take those numbers and learn something on them. Very hand-wavy. A transformer is one of the very popular natural language processing architectures in deep learning over the last 1.5 years, maybe. It's something that Google, like some research that Google came up with. A lot of the models after that have been based on that. But the thing that I want to focus on here is that we can put, for example, we can use a transformer network for machine translation. So we can do things like I'm a student, like feed the French version of I'm a student into the transformer and have it output the English version. So that's all pretty cool in principle, and it looks like nice and fancy and all that. But the problem is that it's kind of hard to get training data for that. So in the previous slide, we had the sentences. You just read it to the on. My French is not non-existent. We read that French sentence, which translates to the English sentence, I am a student. And okay, so now we have one training example. We can get maybe some more training examples by getting translated versions of the European Parliament discussions, for example. I don't know if you know that. The European Parliament posts all their decisions in all the languages of the European Union. So that's one of the very popular data sets that people use for training machine learning. But even then, it's kind of not enough. For example, maybe you can, if you're lucky, you can get 10,000 examples or 100,000 examples. But modern neural networks, for example, the transformer that I mentioned in the previous slide, get trained on millions to billions of examples. So, for example, one of the networks that I'm going to touch on in the next slides was trained on maybe 140 gigabytes of text, just raw text. And that's a lot of data, and it's hard to get that for most actual natural language processing tasks. So, for example, for machine translation, for each sentence, we need to have someone translate it from one language to the other. And then if you want to train the other side of the model, the opposite as well, which we already have that. Anyway, but yeah, it's very hard to get a decent amount of data and train on that. And so one idea that we can kind of use here is, can we use a large non-labeled data set? So can we use, for example, the data sets we're talking about, like Wikipedia or something very with a lot of data, and have that, use that as a basis for follow-up learning. So for example, for machine translation, you kind of need to know, if you're a human translating languages, in addition to knowing how to translate between English and French, you also need to know both English and French pretty well. So can we kind of do a similar thing for computers and use knowledge from an unrelated task? And turns out that we actually can do that. It's called transfer learning. That's a setting in machine learning models where we train a model on one data set, solving one problem. For example, modeling Wikipedia that has a lot of data for it. And then we use the knowledge from that model in order to solve a different problem that's related, but not exactly the same. So the high-level idea here would be something like, we train the model on very large amounts of data so that it understands language, so that it can represent, here's what language looks like. Here's how the grammar works. Here's how the words work, and all that. And then we take this existing knowledge and we transfer it to another task. For example, machine translation or classification of tweets or of IMDb ratings or whatever. And I'm going to show you some networks here. But the idea is that if we have a deep network that has 10 layers, the idea is that we use the large data set to pre-train it, to pre-train all those 10 layers on, for example, the problem of predicting the next word in the sentence, which is a problem that's very easy to get data for because you just get large amounts of data and you feed it into a classifier. You just get large amounts of text, basically. And then you use, for example, the first, here it's the first 3 layers or the 4 layers. But basically, you ignore the last layer and treat it as the thing that was actually solving the specific problem, and take the previous 3 layers, for example, and you kind of count on it being representing the actual knowledge of how language works. So basically, it's we're going to learn how language works, and then we're going to fine-tune, given this knowledge, we're going to fine-tune a different, more specific problem. If you think about it, word vectors, the things we talked about a few slides ago, is actually an example of transfer learning because we can use, for example, a large amount of text like Wikipedia to train the word vectors, and then use those word vectors as an input to the model. But the problem is that if you have a multi-layer model, the word vectors would only be on the first layer. So your model that actually solves the specific problem, like machine translation, would need to relearn everything that's at a higher level of abstraction than words. So, for example, how grammar works is not encoded in word vectors. So if your model for machine translation or anything like that needs to know how grammar works, is going to have to rediscover it. So the idea with actually doing transfer of more than one, like more than just word vectors, but like sentence structures or something like that, is that you kind of embed understanding of grammar and higher level language concepts in that. One example of doing this transfer learning is a model called GPT-2. GPT means generative pre-training by OpenAI. How many of you know what OpenAI is? All right, so for the rest of you, OpenAI is an artificial intelligence research company that was founded maybe 2 or 3 years ago. At that point, it was founded by Elon Musk and a few other billionaires in order to make artificial general intelligence that's like friendly to the public and all that. So they're like working on advancing the state of the art on artificial general intelligence. And basically, a few months ago, they released this model called GPT-2. And they basically said, our model is so good that we think it's dangerous. Why is it dangerous? Because they thought that the model's output is so good, it can generate coherent paragraphs of text, so you can give it like a sentence or two, and it can generate like continuations, paragraphs of text after that, that if you're not careful, can actually be treated as actual word, like content generated by a human. And so like a specific problem with that would be scammers or people who do fake news could use that to actually generate the fake news at very large volumes and very large amounts. So what they did is they did a staged release. They didn't release the model immediately, but rather they released like a much smaller, less powerful version of their model. And they did like after 2 months release a slightly bigger model, and then after 2 more months, slightly bigger model, and then literally last week they released the actual big model. So I'm going to show you a few examples of how this model works. I seeded it with a sentence that should be relevant here. It said, this is a conference in Bulgaria. Like, this is the input that I gave to the model. And then it continued with, a country where the Communist Party still controls the government, and where it is a crime to use a computer without the party's permission. We asked the Bulgarian government for its reaction to the party conference. For some reason, he decided the conference is a conference of the party, and we're told they had no comment. So that also illustrates like kind of the bias that we were talking about earlier. Apparently, the model that they had, like the data that they trained their model on, kind of still had mostly references of Bulgaria in relation to the Communist Party and like still being in that political situation where you can't use a computer and all that, which might apply to different countries in the world nowadays, but luckily it doesn't apply in Bulgaria. But like this is all content generated by the model. So like I went to this site, I entered the input, and I haven't done anything after that. Like I haven't changed, I haven't added commas, I haven't made things into sentences and all that. The model did all of that on its own. And then I wanted something that's like a bit more specific to what we're actually doing and not a party conference. So I did, this is a technological conference in Bulgaria. It continued with something that's actually kind of smarter. Held in the city of Plovdiv from December 6th to 7th. Notice that it does 6th to 7th, so it's like a actually meaningful range. So it's not something like 6th to 4th or whatever. So it kind of learned to model that. It is organized by the Institute for Theoretical Engineering at the Academy of Sciences of Bulgaria. So I checked, as far as I can tell, there's no Institute of Theoretical Engineering at the Academy of Sciences of Bulgaria. So it knows that it's kind of roughly, vaguely aware of the fact that there's an Academy of Sciences of Bulgaria, but it also made up its own institute within that. It sounds legit, doesn't exist, but yeah. The goal of the conference is to discuss theoretical, practical issues. So it kind of repeated itself there, related to artificial intelligence, which is what we're doing now. This year, the conference will focus on the development of intelligent software systems. This will be covered by several speakers from the fields of artificial intelligence, computer science, philosophy, I don't know why philosophy, and more. So again, this is like pretty coherent. If the conference was in Plovdiv and the institute existed, we could have actually kind of used that as a description of the conference for some like subset of the docs in it. And again, this is like completely generated by the model. Okay, so why do I say that this is transfer learning? Like transfer learning, as a reminder, was the idea that we're going to train the model on one data set and then we're going to use it on another. And so far, we trained the model on a large body of text, and then we asked it to generate text, which is like pretty similar, like almost the same problem. So why do I say it's an example of transfer learning? It's actually like an extreme example in that it does what's called zero-shot learning. Zero-shot learning is like a very nice idea, which is that instead of taking the model that has all this language knowledge and then fine-tuning it for a different problem, we're actually not going to fine-tune it. We're just going to say, oh, you should be able to do just fine on that training data. So they basically take the model that's like trained to generate text, and they try to experiment with it on different problems. And one example is they trained it on question answering. Question answering is one of the problems in natural language processing that has been kind of big lately, for the reason that it can be used for chatbots. So you can create a chatbot that takes answers from someone on a website, takes questions from someone on the website, and then generates answers, and then save some money on support, for example, or something like that. So it's like, it's big, but it has the same problems that I mentioned earlier. It's kind of hard to get enough labeled data. So what they did is they just fed in the questions, and they said, who wrote the book, The Origin of Species? And the model just generated Charles Darwin, because it's like apparently it's seen questions and answers like this in the text. Like they didn't do any task-specific training. They didn't train it on questions and answers and like having the model actually generate answers. They just fed, like this is the language generation model. I'm just gonna feed it with a specific question. So they fed a question and it actually answered, and it's correct. The other example is, what is the largest state in the US by land mass? The correct answer is apparently Alaska. The model answered California. And again, I want to mention that this is like the generic model. Like it wasn't trained on answering questions about states or geography or even just answering questions. It was trying to just generate data that like language that seems coherent. And it managed to generate an answer that's like a single word, and it is also actually a state. So it was kind of aware that it needed to generate a state for this. It just generated the wrong one. So like the word representation was not great. Okay. So I figured it would be pretty great to do a demo with Bulgarian language on this and train it on Bulgarian texts. That seemed like an appropriate thing to do. So I started researching how do I train this model with Bulgarian text. Because, like I said, they just last week released the actual English model, the full-sized one. So it's actually like not entirely a trivial exercise to generate this at the moment. So I was like, okay, I'm going to do some research, and then I'm going to do some training, maybe loan a GPU from Google Cloud or something like that, and train this for a while. It was looking good. There were some places that implemented the model and all that. And then I stumbled upon this, which is like this Julian guy is a CEO of one of the popular NLP companies lately. It basically said, order of magnitude of the compute cost of pre-training a large model is anywhere between 10K and 100K. And that's for one pre-training, and usually you really want to run multiple ones to like get a better model and all that. So I was like, okay, I'm not going to spend 100K on this, so we're going to have to do without a model. But actually brings us to a next pretty cool idea that I'm also like personally very excited about, and that's something called cross-lingual transfer learning. So basically, the idea is roughly the same. We're going to do transfer learning. We're going to take the knowledge that we have from one task and apply it to a different one. But here, instead of changing the task, we change the language. So it's basically like saying, I'm going to train a model that can, for example, do sentiment analysis on English text. And I'm going to do that, and then I'm going to use it to do sentiment analysis on Bulgarian text. Because I probably don't have enough training data for the Bulgarian texts, because no one has done enough sentiment analysis, no one has labeled the data sets and all that. So what I'm going to do is I'm just going to use the English model, because it's like way more powerful. And what you see here is an example from a recent paper by Facebook. The idea is that they took what is that, Spanish? Anyway, they took the word vectors, like they generated the word vectors for two different languages. And then they realized that the spaces with the word vectors have like kind of a similar structure. So they're not exactly the same, but they're similar. For example, they know that's again, this is a simplified example. It's in 2D. It's a drawing that has like 15 words in it instead of like 50 million or whatever. But they basically found that the structure of the two spaces is similar enough that they can use some mathematical optimizations on the word spaces in order to align the words. And basically what they end up with is the word for cat next to get all, which is the word for cat in the other language that they were training with. And basically a lot of the words actually end up aligning in that sentence, in that space. So you train on English data, then you train on Spanish data. And in this particular paper, they didn't even have any kind of dictionary. So they didn't know, oh, these 100 words in English and Spanish align with each other, so we're going to align them. They didn't even have that. They just used the mathematical geometric structure of the spaces and aligned them to get this word alignment. So that's pretty awesome. And then another thing that's also very awesome is that we can take this idea of word vectors and use it for other things in addition to words. So for example, we can use word vector. We can actually use sentence vectors, so like sentence embeddings. So you can take the sentences that we did before, dogs love walking and dogs love running, and turn them into vectors that represent the whole meaning of the sentence. And in a perfect world, the distance between these should be kind of small. And it turns out that actually, you can do cross-lingual sentence embeddings. So you can do a model that takes sentences, translates them to vectors from multiple different languages, and have those align and be close to each other in the embedding space. So I'm going to try to show you a demo with this as well. See if it's going to work. So okay. We have these, I think I only trained it with these 5 sentences in the beginning. So I turned these 4 or 5 sentences into vectors. And then what I did was I wrote a function which takes a sentence, converts it to a vector, and then finds the closest vectors, and so basically the closest sentences. And so I can do things like find the closest sentences of the sentence, the dog is blue. And it says, oh, the cat is blue is actually a pretty close sentence to that. And then we have the dog is brown, is like close but not as close. And then we have the coffee is brown, far away. And then we have don't forget the alphabet for some reason. I put this there. But basically, this is like even farther away. And then if we do the dog is black, we have the dog is brown as the closest answer, and then the cat is blue. Then we do the alphabet is unforgettable. It's like kind of a similar sentence, so we get never forget the alphabet. And then here comes the part that I think is like very awesome. Then I did find closest to this English sentence. Don't forget the alphabet. So like there's no machine translation underneath. It's just like we use the model to generate a vector for this sentence. And it ends up in the same space. And the model can tell us that don't forget the alphabet is actually the closest sentence to that is like Nikugan is about like the Bulgarian version of that. And like, again, I just want to emphasize this. Like the model learned all of this on its own and like managed to put all of like the multiple different languages in the same space. If I do, how do you do French? Anyway, I'm not sure I'm going to be able to put an actual sentence together in French. Like if I do something like this, which I'm not sure is, like it's kind of a word. Just want to see if that works. All right. Okay, so we did actually get the sentence with the dog. So this is a model that can do this for like close to 100 languages total. Okay. I want to give you one final example. Yeah, like a very cool thing is that the model was never actually trained on French to Bulgarian data. It just learned on its own, like based on the other languages that it was trained on. So it's like, it's actually even zero-shot learning, like the thing that we discussed before, where you train on a sentence that's not exactly on a problem that you haven't seen before, across languages, across language pairs, and even across language families. And just like one sentence on limitations, that's another example that I generated from the model, like the GPT-2. It's like kind of realize one problem with these kind of models is that sometimes they can go into a repetition mode. So it's at this is a technological conference in Sofia, and we're taking place in the same place. And then this is a cultural conference. This is a cultural conference in Sofia. This is a cultural conference in Sofia, and we're taking place in the same place. So it kind of went into a loop. So basically, like the theory there is that we haven't actually solved language yet, even though these things like seem very advanced and all that. Cool. Thanks. That's all we got. And I don't think we have time for questions, but like, okay. I guess we have time for questions if someone has like one or two. Okay, we can do questions. Cool, thanks everyone.